In this demo, we're going to have a look at a viewport class in Android and to briefly go through how it works, how it operates. And by way of a little bit of, I suppose, background or context on this, because there'll be a little bit of something that can confuse us in it. It ties into coordinate spaces. So in this here screen, you can sort of see two different ways of representing a two-dimensional space. And the image over on the left-hand side is how we normally think of a two-dimensional space. So we have an origin point, 0, 0. Generally, we have an X and a Y axes to map out space in that particular region. And a positive X direction, so increasing X moves us normally to the right, and increasing Y normally moves us up. And that's, if you like, the standard convention. In terms of drawing to the screen, so if we're thinking about the screen as a two-dimensional array where we can draw and highlight certain pixels on it, for the screen coordinate space, for an old historical artifact based on cathode ray tubes and how they were actually originally lit in terms of scan lines, it's different. So 0, 0, the origin, is the top left-hand side of the screen. Positive X still points to the right, but positive Y now points down the screen. So if you're moving in an increasing Y location, visibly we will see that as a downward motion on the screen. And it's the fact that we have these different ways of modeling space that will or can introduce some complexity into it. The reason for this is that most generally, if we're thinking about our game and we're imagining the game in our heads and we're thinking about how objects are moving and giving them velocities and things like that, we will want to keep to our normal conventions that positive Y is up and positive X is to the right. But we have to remember then when we're drawing out to the screen to swap those things around, that if we want to give that appearance on the screen, the Y coordinate in particular is going to have to be modified ever so slightly. And it's a small tweak, basically it's just taking away from the top of the screen and then it'll hold together. So I'm going to show you a demo. Inside the demo, what we will have is a world, and I'm assuming in our world we're thinking about the world in the normal way. Actually, I'll show you two. I'll show you one where positive Y points up in the world, which would be the normal convention, and a separate implementation where positive Y points down in the world. Now, if we go on the second one where positive Y points down, it'll make it a bit more difficult for us to imagine it in our heads, but it means that drawing it onto the screen is actually more straightforward. But I would suggest we want to stick with the normal convention that Y points up. So I'll show you two worlds. One of the worlds, positive Y, will be pointing up. And inside both worlds, we're going to define a number of rectangular platforms. Well, there will be a graphic image for them, but they will be set out as basically platforms with a rectangular bound to them. We're going to have a viewport. This will be a layer or a game viewport. It is the window into our world. So we will position our platforms in space. And there's going to be, depending on the viewport size, but we'll set up a viewport which will only let you see a bit of the world. And we're then going to have that viewport move in a positive X, positive Y direction through the world. So we will get to see different regions of the world. And as a reminder for I'll show you two worlds, positive Y being up and positive Y being down. If positive Y is down, then if I'm moving in a positive Y direction, I'll be moving down the way in terms of the viewport. So we will have one layer or one game viewport, and the contents of that viewport, so whatever is displayed in the viewport, we will then be displaying on the screen. So we will get to see all of the different rectangles that are visible within that. That's the bits actually we will be drawing to the screen. So that's what we want to try to achieve. In terms of the demo that does this, it's within the demo package inside graphics, inside Viewport Test fragment. And I'll just run you to give you a view of this. So it's under Viewport Test. So if we run with Viewport Test, we can see here where we have a world where we have a number of platforms, and this sort of floating island type platforms that have been set out. There's two worlds. So we have one where positive Y points up, and that's what you see in the top half, and one where positive Y points down, that's what you see in the bottom half of the app. So for both of those, just to go back again to from the start, they actually are mapped, they're aligned with one another. So there's two worlds. You can see there's four, if you like, displays here, and we will have then four screen viewports. So the content, if you look at the top two viewports, the content is the same, and what we're doing there is that we are taking our one window into our world and drawing it to two different screen viewports. This is just to illustrate that we can do this, we have this flexibility, and the viewports differ in terms of their size. And the one at the bottom, which is sort of slightly getting off sync with the top one, that's just due to an integer arithmetic. There again, the content is the same, but they are moving in a positive Y direction, being down. So we're going to have a look at this. Now, inside the viewport test fragment, there's a reasonable amount of code which we want to step through, but at a high level, which we'll do this initially, it's fairly simple. We're going to have a game world, so basically this is where our platforms live, and we'll have one where positive Y points up, and we'll have exactly the same game world, the only difference being that positive Y points down, but otherwise the game worlds contain the same contents. We will then have a render view. This is the screen, the thing that we're rendering to, and inside that render view we're going to have a total of four screen viewports, two for their upwards facing world and two for our downwards facing world. We'll have a look at the different methods within this. But some of the things I can do, so for example, if I were to go into my game world with a positive Y points up, and we'll have a look at this in a second, there will be a bit within this where I'm creating my layer viewport. So this is the world into which I see, and I'll show you the box class in a second, but the four parameters are the X and Y, the center point of our layer viewport, and then the width and the height. So I could change, for example, this to be 600 by 600, which means I'm now seeing a region of the world that is bigger. And if I run that, I'm gonna let the thing be pushed out to the emulator. So in this sense, I've gone from having a 300 by 300 window into our game world into having a 600 by 600 image window into our game world. So if we run the viewport test again, you can see now that we're seeing more of the world. It doesn't change the screen viewports, they remain the same. These are independent things, this is where we're drawing to, but the amount that we're drawing is determined by our layer or our game viewport. So we've made that bigger, which means we get to see more of the world. And again, you can compare it with the one at the bottom, which is still using the 300 by 300 viewport. Now, you can do lots of things with this. You can sort of zoom in and out of the game. You can change it. It gives you a bit of flexibility over how you sort of visualize that. Beyond that, the other things we could do, let's say we go down into our render view. Render view, again, we'll go through this class in a second. It contains the screen viewports. So we have four of them. Now these are rec. I'll look at that class as well as the built-in Android one. So you have a top left location and you have a bottom right location. And at the minute this is going from 50-50 to 500-500. It's a 450 by 450 rectangle. Now I could change that to, let's say, 200. And we will then, let's push that particular one out. So in this case, we're going from having a 50-50 to 500-200. So that's 450 across and 150 down. And if we run this, whenever it fires up, we can see then that we've gone back, well, we're still sticking with our 600 by 600 window, but we've changed one of the screen viewports. So our 600 by 600 is it's a square shaped, and the viewports that I did have on the screen, they had been square shaped. Now on the one that's in the top left hand side, it's more of a rectangle. I'm squishing the y-axis on it. So I still take, if you like, my 600 by 600 content in my game, but I'm now compressing it onto a smaller region on the screen. So we've got a lot of flexibility over this in terms of how we can use this to give different windows into our world, and also use this to control which regions of the screen we are ending up drawing to. So let's have a look at the actual code within this to see what it is doing. We'll start off first of all probably with the way that you won't want to do it, where we will have positive Y points down. So it maps onto the screen, but it doesn't actually map onto how we most naturally think about our world. But we'll have a look at this as our starting point, and we can then compare and contrast the changes if we want to swap it around, so positive Y points up the way. So it's done in a private class, and ideally, yes, I stuck them all in the same class here just to tie everything together. In a proper game, you're going to have these things extracted out into their own classes. So game world, positive Y points down. Inside this, we are declaring a number of platforms. There's a total of 100 platforms that are set out that we move our viewport, and we're getting to see those. So if I let the demo run on long enough, we would leave the 100th one and you would see nothing then in the world. We're storing these in an array of rectangles. Now, rect is the built-in Android class, and the thing to remember about this is that for a rectangle, it is actually set up with the same concept that it is an on-screen rectangle. So it assumes that the top, visually when we're looking at it, the top of the rectangle will have a Y coordinate which is smaller than the bottom of the rectangle as it appears to us. So effectively positive Y points down the way. Anyway, we'll declare an array of those, and we're going to have a bitmap that we'll draw to actually just to show each of the rectangles. Notionally, that's what's going to illustrate the content of them. We're going to have our layer or our game viewport, and this is just simply going to be a rectangle as well. So we're saying we have a rectangle, and whatever we define within that region, within that rectangle, that will give us our window into our world. So here we're using all of the built-in classes. We don't need to change them to anything else because all of the default classes that we get do assume positive Y points down the way. We'll construct it, and in constructing the world, we're going to create some viewports, and we're going to then load in the bitmap and create these platform objects just to position the rectangles. For creating the viewport, this is very straightforward. We're going to have our viewport class, and we'll sort of look at this one in a second in terms of the structure. But again, it's a rectangle. We're passing in here the top left and the bottom right coordinates. So our rectangle starts at 0, 0 and goes to across to 300, 300. So that's the size of our world view. And if I change this, for example, to 600, 600, then I would, similar to what I showed you when I run the thing, you get to see a larger region of the world. So that's a rectangle, that's the setup, nothing more than that. For loading and positioning platforms then, this is fairly straightforward. We're going to our asset manager, trying to load in a bitmap, hopefully it'll work. Having done that, we're then going to go through our array of platforms and position each platform. You can see where we work out the X and the Y coordinate here. So we're positioning them notionally so that one box is on top of the other. So they are separated out, if you like, along that 45 degrees along that particular line. So that positions those objects within the world. And that's our setup. Now, we're viewing this as our world. It's a simple-ish game here. So we will update and we will draw. For the update method, we're setting a scroll speed, and we are using that scroll speed to change the location of the viewport. So we're moving our viewport, and we're moving our viewport along. Well, it depends on the bitmap that you load in, but it tries to follow along the line, the layout that the bitmaps actually have. So we're moving it along the X location, and depending upon how big or wide the image is, the ratio of it by a certain amount down as well. And this maps onto how we set the thing out. It's a little bit of integer arithmetic here in terms of the divide, which means that you actually get a small amount of inaccuracy coming into it, because a rec class, RECT, uses basically integer values specified as part of it. So doing this particular thing here, if we don't get a clean division, we'll have a small error, which means over time, actually, we're going to be slightly off in terms of our tracking. And you actually see that when you run the demo. If you let the bottom ones run for a long time, the viewport will actually move off the line of platforms. Way to get around this would have been actually to use proper float arithmetic, floating point arithmetic, or to have a bitmap where the ratio is 1, or a clean number in terms of width compared to height. Now, having done that, then we do one final test here to see that if we do get down to the end, we're going to jump back to the start, so we'll sort of loop around the view. That's our update. The draw then, so the draw thing here is where all the complexity, I suppose, comes into it. We're going to have 2 rectangles, and this ties onto the lecture, so I'll go through this reasonably quickly. We will have a source rectangle, and we'll have a screen rectangle. Now, as a reminder here, we've got our viewport, which is our window into our world, and we've set up things to have a certain size. The source rectangle is going to be the region of the bitmap that we're using to draw each platform that we want to have displayed on the screen. So that's our source data, respective or relative to the bitmap. The screen rectangle is going to be the area or the region on the screen that we want to draw that bitmap to, or that part of the bitmap to. So our goal here is to calculate the source and screen rectangles. We've got our draw method. So in the draw method, we will be told, well, here's a canvas you can draw to, it's going to be the screen, and here's the screen viewport that you should respect. So this is the thing that we are drawing the different bits into. So when we might be able to work out, or we will be able to work out, if I have my layer viewport, this is the region of the bitmap that falls within it. But I then next want to work out what region of the screen I draw that onto. And I'm restricting it to whatever the screen viewport has been declared to be. Now, then what we have down here is similar to the stuff within the lectures, but arranged a bit differently. We're going to do scaling from the screen to the layer viewport. When I changed the demo, and you saw the second viewport where I changed the on-screen rectangle and it looked squished, this actually would have changed the Y scaling. That would have gone from having a certain height for my screen viewport, maybe my screen viewport is 150 pixels high, but my layer viewport might be 100 units high. So this gives me a way of mapping from the layer coordinates onto the screen coordinates. I know that if I move 1 unit within my game world, I can work out then how much that correlates to in terms of screen movement in terms of pixels. So that gives us a way of mapping from one to the other. Now, I do that at the start because for all of the platforms, this is going to be invariant. I'll work it out once and it's going to be the same mapping for every single thing I draw within that particular frame. I then go through each of the platforms which we're drawing out. We've got our initial collision test here. So this is our test to see, does the rectangle that we have for this particular platform fall within the viewport? And if any of these, again, as we looked at in the lecture, if any of these conditions are false, it means that it can't possibly be visible, so we don't need to even bother trying to draw it, we'll get out. If all of them are true, it means either all of it or part of that object falls within the viewport, so we have something to draw. Down here, we're working out the source. Similar to for the screen to the layer, we want to work out that if I move 1 unit within my game world, how many pixels within the bitmap that I'm going to draw that object out does that correspond to? So if 2 units of the object are visible within our game viewport, I can work out how many pixels within my bitmap that I have available I need to draw. And admittedly for this one here, I'm just using the same bitmap for all of them, so actually this could have been something that went up to the top, but because I'm assuming here platforms might have different graphics, the ratio could be different, so you still want to keep it within here. So we do this here, we work out, okay, how wide is the bitmap, and how wide is this platform in terms of game units, and that gives me my mapping then. So do that for the width and the height, that's my scaling. Now, the bit after this down here is where we then work out which region is visible. And we talked about this in the lecture as well. So we're using the first one for doing the source X. So either now source X in this case is the starting point of the rectangle, which will be the left-hand side of the rectangle. Either the left-hand side of the rectangle is somewhere within our viewport, so it's visible, or the left-hand side is off the viewport, but a bit of the image actually is still visible on it. So this is the initial check that works out, okay, whereabouts do we start from in terms of our object? This is expressed in game coordinates. And we do the same for the Y as well. So this is the first bit of our game that falls within the viewport. We then calculate the width and the height. And again, these are in terms of layer coordinates. So if we say that in game our character is 10 units wide and 20 units high, doesn't matter how many pixels we have in our bitmap or what we're drawing onto the screen, this is thinking about the size of our character in the game, then this will tell us the width and the height in the game that actually is within the viewport. So once we've done those 4 different lines, and these are, because the rectangle positive Y goes down and our game world positive Y goes down, these are very straightforward lines. When we swap the thing around where we have positive Y pointing up, we're going to have to sort of tweak the odd line here. But for this one, it's straightforward calculation. So it's worthwhile going through these, just look at the different bits to get your head around those. We then set our source rectangle. So this is the source rectangle that contains the region of the bitmap that we want to draw out. So you can see here we're using the source X, source Y, source width and source height that we calculated, which were based on our game world coordinates, and we're then multiplying those by the scaling factors that enables us to convert from a game world into a bitmap that we have available to draw out. So if we work out that we want to draw a 2x4 region in our game world space, we'll work out then how many that source pixels that corresponds to within the bitmap that we have available. Having done that, we're going to do more or less exactly the same thing with working out the screen location. So in this sense, the screen location, we have to start it from wherever the screen viewport begins. We're not drawing outside of the screen viewport, we're going to draw within the screen viewport. So our starting point is always going to be the left and the top hand side of the screen viewport. That's where we begin relative to the overall screen. And we're doing exactly the same types of calculations, except in this time we are applying the screen scaling to it. So same calculations, but now we're working out in terms of the screen coordinates whereabouts we are going to draw that bitmap to. Do the same for the width and the height. So we've calculated it for our source and we apply our screen scaling to that so that it will scale it up or scale it down depending on the pixel density of the bitmap and the screen. We set up then our screen rectangle, simply putting in the pieces that we have. And the final one then is we go to our canvas and we're saying we don't need to draw out that bitmap. Here's the source rectangle for that bitmap. And there's the screen rectangle that we're drawing to for that particular canvas. So a little bit complex because you have these conversions from different coordinate spaces from our world space into the bitmap space onto the screen space. And it's useful to get your head around those different aspects in terms of what it does. But that will enable us then to draw it cleanly within the region that we have on the screen. That is effectively our world view where positive Y points down. I'll show you the view class, then we'll go back to our positive Y points up. So within the view class, this is basically going to be the thing that will constantly redraw out the world. So we have a total of 4 rects. So these are, again, the on-screen rectangle, positive Y points down for the different regions. In our render view, whenever we're creating this, we actually will define the 4 different screen views. So I mean, normally you're just going to use one for the whole screen if it's a whole screen game. If you're doing a split screen, you'd have maybe 2 viewports, one for each sort of side. You can do it whatever way you want to. For the on draw, now I've been naughty here. Generally, when you're drawing, you just want to draw the world and you have a separate update method. For this demo, I'm not putting in a full game loop. So basically, when I'm drawing this particular canvas, I'm going to update my two worlds. Really should have an update loop for doing that. And I'm then going to go to the worlds and ask them to draw themselves into the canvas and tell them to draw themselves into two different on-screen bitmaps or viewports. Then I'm going to go to sleep for 30 milliseconds. Then I'm going to invalidate myself. Now, because this is on draw, if I invalidate myself, I'm basically saying to the user interface thread, hey, draw me again. So roughly sort of 30 odd times a second, this thing will end up redrawing itself and trying to redraw itself. Where we update our world, which moves the viewport, and we call the draw method, which results then in what is visible in the game viewport being displayed on the screen viewport. So that's fairly straightforward. Now, the last thing here we want to have a look at is our game world where positive Y points up. Because that's going to be the more natural way of thinking about things. And I'm declaring, same as before at the start, I've got my 100 platforms. I've got a change here. So before, when Y pointed down, I used the rect class, the built-in rect class, because that assumes positive Y points down. I can't, or I shouldn't use that if I want to imagine positive Y pointing up the way. So I've put in a new box class. And it's declared up here. And I'm going to use this class under the assumption that positive Y points up. And I've also made a few other changes here. So, you can specify boxes in different ways, top left, bottom right corner. The way I generally think more about objects and their location is that they have a center point and they have a width and a height. So I've created my box class, which has an X and a Y. I'm using floats as well because you get smoother movement as opposed to integer classes. So this will give you more smooth motion and movement within your level. X and Y then is the center location of that box. The width and the height again is floats. They are how wide and how high the actual box is. Simple constructor where you can specify the thing. So the box class, not really much to it. Nonetheless, that's what we use for creating the location of the different objects within the game. We've got a viewport, and before I used a rectangle class. Here I want my positive Y to point up. I'm going to use another box because that serves the purpose. My viewport can have a center, can have a width, can have a height. Also works out. Similar to before, I'm going to create my viewports, load the things in. For creating the viewport, as opposed to creating a rectangle, I'm creating a box, where I'm saying the box is, its center is at position 150, 150, and originally, before I changed it for this demo, it was 300, 300 width and height. So actually it was the same size viewport as in the other demo where positive Y pointed down. For loading in the things, exactly the same as before, we load in the bitmap, and we are creating the boxes. Okay, so I'm given the center location, I'm given the width and the height of them, so a little bit different, but they're positioned in the same notional setup as in the other demo. For updating it, again, it's the same idea. We are moving the X and the Y location of the viewport and scaling that by the width and the height of the platform that we have between it. You can see here that I've casted them into floats. Because our box is using floats as opposed to integers, I can take I can get a sort of a proper or more accurate ratio between the width and the height. So I can have 2.3 or whatever it's going to be. This means then that, again, you can see this when you run the demo, when you're using the box because it uses floating points, it does actually track the boxes a lot more smoothly than the bottom one where you have integer arithmetic, small errors being introduced every single frame. For drawing it out then, now we want to draw to the screen, so we're still going to draw through our canvas. And that means that if we want to draw to the screen, we have to use rectangles. Well, we don't have to use matrices, but we're going to use rectangles as the area to determine the source and the destination rectangle. So we are still using rectangles here, and it's still the same to source and screen rectangle. Just a reminder, the reason we're doing this here is because we're drawing to the screen, and the screen uses a canvas where positive Y does point down in the screen. We can't change that. And we're going to use the rect then because that's what maps onto it. That's what the Android developers have assumed we're going to be using. So we have exactly the same problem as before in terms of how do we populate these. The process actually is going to be the same, but there'll be a few key points where we swap the X and the Y, or sorry, the Y around in terms of the order in which we're doing it. So we calculate the scaling between the screen and the layer viewport, same as before. That doesn't change. We're going through each of the platforms and we're doing our same type of test here. So it is exactly the same test as before, but as opposed to using a rectangle, we're using our box class, but it's the same notion of if part of it falls within, we want to draw it. We're doing exactly the same type of scaling as we had before between the bitmap and whatever game size that platform has. That doesn't change. And there's a little bit of change down here. So for anything to do with the x-axis, it isn't going to change. So x, always positive x points to the right. So anything about the x or the width unchanged to the previous one. For the y one, it will change ever so slightly, and because positive y points down the way. So it's going to be useful just to sort of have a look at the positive y being up, positive y being down, and to see the differences between them. But in essence, we're doing the same types of calculations about working out which bit falls within, how much of it falls within, and then setting up the source rectangle for it. But in setting up the source rectangle, we have to remember we need to swap the y coordinates around because positive y points down. So we take that into account. For doing the screen coordinates, same process as before then, where we're again starting from the left and the top of the viewport, and we're working out the width and the height of the region we can do. So this doesn't really change very much, same applying, scaling is applied. Screen rectangle, we set it up again the same way as before. So at this point, largely we are working with rectangles on the screen, so that doesn't need to change. It's only when we put our box in and are converting into a rectangle that we have to remember to swap them around. And then finally, we draw it out to the canvas, same way as we did before. And that's more or less it. So viewports, depending on your game, if you need to use a viewport within the game, they are very capable, very powerful things. They do give you your window into your world. It's worthwhile spending a bit of time getting your head around the conversion from game space into the space of our bitmap onto screen space. And also worthwhile getting your head around how we can convert from thinking of it as a positive y being up to a positive y being down. That sort of handles a lot of the complexity. And it means then it's a bit easier for us to imagine how we will go about creating our game.